This is Chapter 20, Microbiology 230. I'm Dr. Croft, and this is going to be on antimicrobial medications. We're going to look at the application of medications and how they help to control growth, if you will, and kill off bacteria inside the host. And I say host because we don't just use antibiotics for humans, we use antibiotics for animals and other things too. So we really talk about that application. We talk about it goes to history in this particular chapter. Paul Ehrlich, who lived between 1854 and 1915, he was a German physician and bacteriologist. He observed that some dyes stained bacteria but not animal cells, indicating that there were fundamental differences between the cell types. So he searched most of his career for the magic bullet that would kill microbial pathogens without harming the human host. He synthesized arsenic compounds to treat syphilis caused by the spirochete treponema pallidum, and the 606 test a compound proved effective in laboratory animals. So arsphenamine, named salvarsan, potentially lethal for patients, but did cure infections previously considered hopeless. And for some chemicals, can selectively clear microbes. So the problem is that it had a high toxicity rate for humans, but it could cure them. And so if they could live through that, they could make it. So the importance of antimicrobial medications is imagine a world without antimicrobial medications. For instance, the prognosis for people with common diseases, for example, bacterial pneumonia, severe staphylococci infections, is grim before penicillin in the 1940s. The #1 killer of mankind before the discovery of all the antibiotics was really infection. They'd get a cut or they'd get a wound and they would die of infection. So physicians could identify the cause, but really treatment was usually bed rest and application of heat and those kind of things. Misuse coupled with evolution of microbial resistance threatens these medications today because we misuse them a lot. There's a really good study if you ever want to look it up. It's called the SIP study, which came out of the University of Oklahoma, Surgical Infection Prevention Study. And strangely enough, my name's on there. It looked at preventing surgical infection. And the interesting thing about it is that the surgical infection rate, like I said before in a previous lecture, is really more related to what happens in the operating room than it does for the surgeon themselves. It's not bad the surgeon is sloppy and creates infections, usually that the infection is inside the operating room already, or inside the hospital when they're recuperating. And so what surgeons have come to do, or came to do before that happened in the late 1990s, is they would give patients these large doses of antibiotics that after the surgeries, particularly ones that were major surgeries, like post-cardiac surgeries and GI surgeries and OB/GYN surgeries and orthopedic surgeries. And so they thought that was helping. The studies show that doesn't really help. Strangely enough, what they found is that, think about this, when you go and do surgery, you make a cut. And you do your surgery, and you suture things together. So there's a clot there. And the clot is the point where the infection can occur, but there's nothing there preventing the antibiotic from getting there. And so if you give them antibiotics, there's no circulation to the tissue where the infection can mostly occur. So giving them antibiotics afterwards doesn't really help much in the long run. They discovered that if you give antibiotics just before the surgery and you have the antibiotics circulating in your system, that when the clot formed, the antibiotic molecules would be included in the clot and they'd be much more preventative of causing infection. So the surgical infection prevention study proved that that was true. And so that was one thing that really helped. And so now we're not putting people on these long courses of antibiotics after surgery when it really doesn't help. We're just using it before the surgery. We may put them on antibiotics a couple of days after surgery in some cases, but mostly what we're doing is we're going to do it just before the surgery. So it's more effective. The second thing that happened is that many patients decided they needed to have an antibiotic for everything, any virus, whatever, and they thought that would help. But the truth is it didn't. So they took antibiotics for infections that weren't bacterial, and the antibiotics didn't help, and so they developed resistant bacteria. And so through that process, if patients did to a doctor, and the doctor said, well, it's a virus, you don't need an antibiotic, many patients would leave that doctor and go somewhere else. So for doctors, it was a financial decision, and many of them succumbed to the fact that they would just give the patient antibiotics and move on, thinking there was no harm done. In truth, lots of harm was done in this process. So the discovery of antimicrobial medications, salvarsan, Paul Ehrlich in 1910, was the first documented case. Red dye protosil was done by Gerhard Domach in 1932, used to treat staphylococcal infections in animals. There's no effect in the test tubes. The enzymes of blood split to reduce sulfonamide, which was really the first sulfa drug. Now both are chemotherapeutic agents, chemicals used to treat disease. Antimicrobial medications are antimicrobials. They're not antibiotics, which means they're not biological elements. They use chemicals to treat it, or chemotherapy. Discovery of antibiotics in 1928 was by Alexander Fleming, who identified a mold penicillium, which excreted a compound which is toxic to Staphylococcus. And he named it penicillin, and it showed it was very effective in killing many bacterial species. It was hard for him to purify. He later abandoned the research. But penicillin was actually discovered by Alexander Fleming. Now, it's interesting because you have to think about who's the first person that took this mold to treat a disease. I mean, who would be that person, right? Kind of interesting. But 10 years later, Ernst Shane and Howard Florey, they purified and tested compounds in 1941 on a police officer with a life-threatening Staphylococcus aureus infection. The patient improved dramatically within 24 hours, and so they could produce a supply of purified penicillin, which finally ran out, and he later died. So it was hard. It was a difficult process. With the advent of WW2, World War II, it spurred research and development, and developed what was called penicillin G, was the first antibiotic. It was a naturally produced antimicrobial. Now, soon thereafter, Selden and Wakeman purified streptomycin from the soil bacterium and developed streptomyces from the soil bacterium from Streptomyces griseus. Researchers screened hundreds of thousands of microbes for antibiotics. The pharmaceutical companies examined the soil samples from around the world and discovered in the 1960s that altering the structure of penicillin yields new medications. So they were able to take penicillin and make it into a different antibiotic, a different antimicrobial, based on making some changes in its chemical structure. So we looked at characteristics of antimicrobial medications. We have to look at what's called selective toxicity. And the goal is that it causes greater harm to microbes than it does the host. So it interferes with the essential structures and properties common to microbes, but it doesn't adversely affect human cells. The toxicity is relative and is expressed what's called therapeutic index. The lowest dose toxic for patient and the dose used for therapy. So that's the dose we look for. Penicillin G has a high index. It interferes with cell wall synthesis of microbes, but it's a process that does not affect humans. So medications too toxic for the systemic use may be used topically. One of those is bacitracin. Bacitracin is a common antimicrobial used in ointments, topical ointments, but it's very toxic to the body internally. So antimicrobial actions can be bacteriostatic or bactericidal. Static, if you remember from a lecture many weeks ago, is a process. Static means the chemicals inhibit bacterial growth. What it does is it stops the growth of vegetative organisms, but does not kill all the organisms. So the patient's defenses must still eliminate the bacteria, as opposed to bactericidal, where the chemicals actually kill the bacteria. And sometimes it's only inhibitory. So basically, bactericidal means it kills all the bacteria. Bactericidal means it stops the growth of bacteria. Now, the spectrum of activity, broad spectrum antimicrobials affect a wide range. They're important for treating acute life-threatening diseases, especially with no time for a culture for identification is possible. And they disrupt the normal microbiota that help in keeping out pathogens, so they can be destructive. Their toxicity can be destructive because they kill off bacteria that are normal in the colon or the other places of the body, and they can cause other diseases or secondary infections to occur. As opposed to narrow-spectrum antimicrobials, they have a very limited range. They require identification of the pathogen, or at least the genus in this case, and testing for sensitivity. They're less disruptive to normal microbiota. But you see that if you have a really urgent case where a patient is really in dire needs, that you're more likely to use a broad-spectrum antimicrobial and hope for the best than to wait until the cultures are done 2 days later and find out the patient died, which obviously the best answer is not that the patient died. And so the effects of combinations, some medications interfere with each other. They're called antagonistic. Combinations where one medication enhances another is called synergistic, and we have that. If you look at penicillin, there's many different generations of penicillin down the line. We have ampicillin, and ampicillin is penicillin with a small change in its structure called a chiral ring. But then we have the next medication, and that medication is called amoxicillin. And amoxicillin is really ampicillin added to another antibiotic called clavulanic acid. And clavulanic acid, what it does is it causes all the bacteria that would start to break up the ampicillin and cause it not to be effective. They attack the clavulanic acid, and it allows the ampicillin to become effective. So it kind of works like a Trojan horse. And so that's synergistic. The combinations that are neither are called additive. So you take two antibiotics and make them additive. Bactrim or Ceftra, which is an antibiotic we use often for urinary tract infections is really a combination of sulfonamide and another antibiotic. So they are additive, if it were. Now we also look at what's called tissue distribution or tissue deposition, and that means how much antibiotic we get in the tissue. For instance, if you take 100 milligrams of antibiotic, you may only get 0.1 milligrams in the tissue. The tissue deposition may not be very good. A good example of how this has hurt us is treating for sinus infections. Sinus infections are infections that occur in the sinuses of the skull, and the tissue penetration, tissue deposition is very low. So if you give somebody a lot of antibiotic, the effect on the sinuses isn't very good. And so we use all these antibiotics to no real success, to be honest with you. And so we learned that we need to do some other mechanical things like nasal washings, if you will. So tissue deposition, metabolism, and excretion. So antimicrobials differ in their behavior in the body. Some medications cross the blood-brain barrier, and they're important in treating infections of the brain and the meninges, like meningitis or encephalitis. Some are unstable at low pH, and they have to be injected, which means you can't take them PO or per os, for the mouth. They can't be taken orally. They have to be injected so they don't have to go through the acid in the stomach. Now, the rate of elimination or half-life dictates how often you use them. So, for instance, let's look at Bactrim, for instance. Bactrim is an antibiotic that's taken twice a day. So the problem is that at 12 hours, it reaches the point where half of the metabolite of Bactrim is now gone. That's called its half-life. And that's the time we then reintroduce another dose. So the half-life dictates how often you take the medication. In the case of cephalosporins, if you will, Septra, I mean, it's not cephalosporins. Cephalosporins tend to be given at 3 times a day. So that's basically every 8 hours they reach their half-life in the body. Also, the kidneys or the liver dysfunction can differ because some antibiotics are broken down the kidneys, and some are treated by the kidneys and broken down by the kidneys, and some are broken down by the liver. So that's pretty important. For instance, this is not an antibiotic, but a Tylenol is broken down by the liver. So if you take too much of it, you'll injure the liver. Where your nonsteroidal anti-inflammatories like Motrin is broken down in the kidneys. And so it doesn't affect the liver, but it can be affected by kidney function. So you have some adverse effects from these antibiotics, for instance. They include allergic reactions and toxic effects, suppression of normal microbiota, so it may allow dysbiosis. For example, Clostridium difficile can become more active and start to create what's called intermembranous colitis, which is a very terrible disease that can cause ultimately a colon resection to remove the part that's been infiltrated by the C. difficile. It's also important to remember that antimicrobials save countless lives when properly prescribed and used. So used properly, they have a great effect. They're very important. There's also a resistance to antimicrobials, which has been a lot in the news of late, and we've caused that, basically. Certain bacteria have innate or intrinsic resistance. For example, mycoplasma that has no cell wall. So penicillin, which is an antibiotic that works on the cell wall, is not very effective against mycoplasma. Same thing with Legionnaire's disease. Legionnaire's disease is caused by Legionella. And they tried to give penicillin and its derivatives to these patients that had Legionnaire's disease, and a lot of them died before they realized it had no cell wall, and so they had to use other diseases. And those are called macrolides, like erythromycin and sulfa drugs and things like that. The outer membrane of gram-negative blocks many of the medications, so that's also something to be important. The bacteria can develop acquired resistance, and that means they develop mutations. They can develop, like if you don't take the antibiotic all the time you're supposed to take it, some of the bacteria may have got a little antibiotic, develop a little resistance, and they continue to grow, and then they are now resistant. You can also send that resistance information to other bacteria, not necessarily their own species, but other bacteria, and make them resistant too. Now, antibacterial medications target specific bacteria processes in cultures. They can work on the cell wall synthesis, protein synthesis, the DNA or RNA synthesis, the metabolic pathways in the cell membrane. So they can work on a lot of different areas throughout the cell. This looks at the mechanisms of actions for those. There's the typical group that we talk about, the different kinds of antibiotics and the comments, the characteristics you see here. And again, I'm not going to go through each one of those, if you will. I'm going to talk a little bit about some of the groups. There's the second part of that. There's the mechanisms of actions. So let's look at the mechanisms of actions, antibacterial medications that inhibit the cell wall. And the bacterial cell walls are unique. They contain that peptidoglycan, remember the NAG, NAB combination, and they're a great target for medications. They often have a high therapeutic index. So penicillins, cephalosporins, and other beta-lactam antibiotics all have that beta-lactam ring. And they competitively inhibit the enzymes that catalyze formation of the peptide bridges between the adjacent glycan strands, and so they disrupt the wall development. And they're called penicillin binding proteins, or PBPs, which sense bind penicillin. They're only effective against actively growing cells. So they're kind of, they're not bactericidal, more they're kind of bacteriostatic if you think about it. They only deal with growing cells. Now, the other medications that inhibit the cell wall include penicillin, cephalosporin, and other beta-lactam drugs, like I said. They interfere with the peptidoglycan synthesis. They weaken the cell wall, it leads to cell lysis. Imagine that they replace a NAG or a NAM with a, imagine this, the NAG or NAM wall, cell wall, is like a brick wall. And instead of a brick being put in a certain place, they take a penicillin or derivative of penicillin, a beta-lactam producer, and they put that in that brick's place. And this brick, though it looks like a regular brick, is really made up of a very soft clay. And so then we wash the wall down, and the wall stays in place except for the brick with the clay, the beta-lactam derivative, and that clay dissolves, and it allows the contents to move in and out of that given cell. So the cell dies, and that's how that works. So like I said, the antibacterial medications in the cell walls, such as include penicillins, cephalosporins, and other beta-lactam antibiotics. They differ in their activity. The peptidoglycan, or the gram-positives, are exposed. The outer membrane, the gram-negative, are blocked. And the PBPs are different in gram-negatives versus gram-positive. Also, aerobes and anaerobes in different species. So the effect is different depending on how these are applied. Some bacteria synthesize beta-lactamase, which blocks the effect of penicillin and the types of penicillins, and it creates that resistance we know as it resists that antibiotic. So it breaks the critical beta-lactam ring, which there have been different types. So penicillinase inactivates the members of the penicillin family, and extended spectrum beta-lactamase, ESBLs, inactivate a wide variety of beta-lactam medications. So gram-negatives produce a more extensive array than gram-positive. So just kind of looking forward as we look at these antibiotics. Now, antimicrobial medications inhibit the cell wall synthesis. Like the penicillins, they share a basic structure. And that is the side chain is modified to create derivatives. So you have a major derivative and a minor derivative. The major derivative of penicillin is really the large molecule. But when it gets to the body, it creates several minor derivatives. And there are 5 general groups of penicillins that are in those minor derivatives. The natural are from the Penicillium crucidatum, and it's it's a narrow spectrum. It acts against gram-positive and a few gram-negatives. Penicillin resistance developed by Staph aureus strains that can produce altered PBPs to which beta-lactam antibiotics do not bind. For example, methicillin-resistant Staph aureus and MRSA creates that environment. So those are resistance to all that. Now, the penicillins share a basic structure that said the side chain is modified to create derivatives, like I said, and some other of those derivatives include the broad spectrum act against the gram-positive, gram-negatives due to the modified side chain, and those can be inactivated by beta-lactamases. The extended spectrum, they have greater activity against Pseudomonas species, like, for instance, amoxicillin, for instance. It has reduced activity against gram-positives. It's destroyed by many beta-lactamases. So penicillins plus a beta-lactamase inhibitor includes an inhibitor to protect the penicillin. And I talked about that with the ampicillin and the clavulanic acid. So antimicrobial medications that inhibit cell synthesis include also cephalosporins. Now they're derived from the antibiotic from the fungus Aceremonium cephalosporium. It includes closely related groups to the Streptomyces. And so the structure makes resistance to some beta-lactamase. So the structure is not susceptible to the enzymes that can break down the penicillins. So it's something we use in place of penicillin if somebody's allergic to penicillin or the infection they have is not susceptible to penicillin. Some have a low affinity for PBPs of gram-positives. The chemical modification have led to 4 generations. And there's 4 generations of cephalosporins. And the later generation is much more effective. It's very resistant to beta-lactamases. Other beta-lactam antibiotics include carbapenems, Monobactams and resistant beta-lactamases like carbapenems are effective against a wide range. Monobactam astreonem, is used against Enterobacteriaceae bacteria. Now, the vancomycin actually blocks the peptidoglycan synthesis altogether. It binds the peptide chain of the NAM molecules. It weakens the cell wall and causes lysis. It's fully absorbed from the intestinal tract, and for that reason, it's usually administered via an IV, except for intestinal infections. It's important for treating gram-positive resistance to beta-lactam antibiotics, and it's also used for severe C. difficile. The antibiotic of last resort, resistance increasing as a problem, and there's a change in the side chain of NAM which prevents the binding. It does not cross outer membrane of the gram-negatives. So bacitracin is one I talked about. The toxicity really limits it to topical applications. It interferes with the transport of peptidoglycan precursors across the membrane, and that's a common antibiotic ointment in first aid emergency ointments. So other antibacterial medications that hit the protein synthesis, and all cells synthesize protein in one fashion or another. But remember, there's a difference between prokaryotic ribosomes and eukaryotic ribosomes. Prokaryotic ribosomes have a 70S ribosome, and eukaryotic cells have an 80S ribosome. So mitochondria also have that 70S ribosome, which may account for some toxicity from the antibiotics. And so you can see that it has a great deal of effect, a different effect on these. This looks at different antibiotics that affect different parts of that given ribosome. Aminoglycosides, for instance, they irreversibly bind to the 30S ribosomal subunit, causing distort and malfunction. It blocks the initiation of translation, causes the misreading of the messenger RNA by the ribosome past initiation, generally ineffective against anaerobes, enterococci, and streptococci because they enter the cells via active transport process. Requires respiratory metabolism. Sometimes it's used synergistically with beta-lactams, which allows the aminoglycoside to enter the cells. But it has a high toxicity level, and it's generally used when alternatives are unavailable. The form of tobramycin administered via inhalation to treat pseudomonas aeruginosa lung infections and cystic fibrosis in patients is safer and more effective, but it can cause otic toxicity, it affects the ears. It's a pretty toxic substance compared to other antibiotics. Tetracyclines are bacteriostatic. They inhibit the protein synthesis. They reversibly bind to the 30S subunit, and they block the T and RA attachment, which prevents translation. They're actively transported into prokaryotic, but not animal cells, and resistance from decreased uptake or increased excretion, and effective against certain gram-positives and gram-negatives. Now, we don't use tetracycline per se now. It's the first generation. We generally now use second generation. That's the doxycyclines. Tetracyclines are poorly absorbed, and doxycyclines are much better absorbed. Now, the glycocyclines are related to tetracyclines. They have the same mechanism of action and effect. They have wider activity. They're effective against many bacteria resistant to tetracyclines, and tigecycline is the only one that's currently approved. So it's one of the newer ones. The macrolides are the antibiotics that not work on the cell wall, and so they are very effective. The erythromycins and the sulfa drugs. So macrolides are reversibly bind to the 50S subunit. They prevent continuation of translation. They often are antibiotic of choice for patients that are allergic to penicillin. They are bacteriostatic, not bactericidal, against many gram-positives and most common causes of atypical pneumonia. They work against strep pneumoniae, they work against influenza, they work against mycoplasma. And the outer membrane of the Enterobacteriaceae is blocked. So resistance occurs from modification of ribosomal RNA target, enzyme that modifies chemical and decreased uptake. And chloramphenicol is bacteriostatic, it's another antibiotic. It binds to 50S ribosome subunit and blocks translation. Now, it's active against a wide range of bacteria, but it's the use of last resort because it causes aplastic anemia, which is a irreversible destruction of blood cells. It's inability to form white and red blood cells in the marrow. Now, antibacterial medications that inhibit protein synthesis include the glycosamides, and they bind with a 50S ribosome subunit, and they block continuation of translation. They're effective as bacteriostatic. They inhibit the variety of gram-negatives and gram-positives. They're useful against Bacteroides fragilis, resist many antibiotics. And they risk development of C. difficile because most strains are resistant. So the thing is that it can literally cause that secondary effect. The oxazolidinones, they bind the 50S-ribosomal unit. They interfere with the initiation of translation. They are bacteriostatic against a variety of gram-positives, and they're useful against strains resistant to beta-lactams and vancomycin. Now, the streptogramins, they bind two sites of the 50S unit at the same time. There are two antibiotics are given. They're a synergistic pair called Synercid, and it's individually bacteriostatic but bactericidal together. So effective against a variety of gram-positives, including some resistant beta-lactams, vancomycin, and inhibit translation. So that's the movement we're getting to the more aggressive. Now, there's antimicrobial medications that inhibit the nucleic acid synthesis. The fluoroquinolones inhibit what's called topoisomerases, and the enzymes that maintain the supercoiling of the DNA are those topoisomerases. The DNA gyrase breaks, rejoins strands to relieve strain from the localized unwinding of the DNA, and the function is essential. So bactericidal against a wide variety of bacteria, and resistance usually due to alteration in the DNA gyrase target. Rifamycins block prokaryotic RNA polymerase, and they prevent initiation of transcription, bactericidal against gram-positives and gram-negatives, and they're very effective against myobacterium like Myobacterium leprosy, and Myobacterium tuberculi, tuberculosis. Resistance can develop in mutation RNA polymerases. Metronidazole, I can't say. It's a metronidazole. Thank you. It's toxic only in anaerobic organisms. Its anaerobic metabolism requires it to convert to active form. It binds the DNA and interferes with synthesis and causes a break. So metronidazole, I can't say it, is that antibiotic. Now, antibiotic medications interfere with the metabolic pathways. There are a few antibacterial antibiotics that interfere with metabolism. Like folate inhibitors are among the most useful, like sulfonamides, trimethoprim, which is the antibiotic that is included in Bactrim and Septra. And so they have sulfamethoxyl and trimethoprim, so they're combined antibiotics that are synergistic with each other. So sulfonamides, trimethoprim, which are the two medications of Bactrim or Septra, same medication, just different brand names. They inhibit the different steps in synthesis of folic acid and coenzyme required for nucleotide synthesis. So animals lack enzymes to synthesize folic acid, and they're required in the diet. The resistance often comes from plasmid-encoded enzymes with lower affinity to these chemicals, and the genes for both often are carried on the same plasmid. So that's one of the drawbacks. Now, the other thing is the interference with metabolic pathways and sulfonamides related are called sulfa drugs. They inhibit many gram-positives and gram-negatives. They're structurally similar to PABA, so the enzyme binds chemically. And it's an example of preventative inhibition. Human cells lack this enzyme. Trimethoprim inhibits the enzyme in a later step. It has little effect on enzymes counterpart in human cells. The combination of trimethoprim and sulfonamide or sulfamethoxyl, that's what it really is, has a synergistic effect. And they're often used to treat UTIs, as I said earlier. Now, there's other ones that interfere with cell membranes. And there are three antimicrobials that damage the bacterial membranes. They cause cells to leak, leading to cell death. They limit the usefulness of topical applications. They limit the usefulness of topical applications. They also bind with eukaryotic cells to a lesser extent. So daptomycin inserts in the cytoplasmic membrane. It uses against gram-positives resistant to other antibiotics. It's ineffective against gram-negatives that cannot penetrate the outer membrane. So polymyxin B binds to membranes of gram-negatives. So this is really a topical antibiotic that is used in those cases, antibacterial. So we look at antibacterial medications that are effective against mycobacterium species. Remember, they have the outer shell, so to speak, and they have that outer layer that protects them from certain antimicrobials. So a few antimicrobials are effective against mycobacterium because they have that waxy cell preventing entry to many chemicals. They're acid-fast outsides, and their growth is slow. So the group of 5 medications are preferred, first-line antibiotics, and they're most effective and least toxic given in combination therapy. So we treat leprosy and tuberculosis in much the same way. So we give them 2 or more, sometimes 2 or 3 at the same time. And it decreases the chance of development of resistant mutants. Some targets unique cell wall with a myobacterium like isoniazid, which inhibits the mycolic acid synthesis, ethambutol, which inhibits the enzymes required for synthesis of outer cell wall components, pyrazinamide, which interferes with protein synthesis. So the second-line antibiotics used for greater strains. They're less effective and have greater toxicity to the human host. Bedaquiline is a target of the myobacterial ATP synthase, and it's really kind of risky to use. We only use it in extreme circumstances. Now, antimicrobial susceptibility is interesting because the susceptibility of pathogens can be unpredictable. They can change from one strain to another. So minimum inhibitory and bacterial cytal concentrations are necessary. The MIC is the lowest concentration that prevents the growth in vitro inside the human being. And serial dilutions of chemicals in suitable growth medium are used in vitro. And so culture is added, incubated, and examined for turbidity. So I'm going to say this again. In vitro means in the body. So inhibition does not necessarily mean successful treatment. The level may not be achieved in the person's blood in vivo. The microbes with MIC between susceptibility and resistance are termed intermediate. So MBC is the lowest concentration that kills 99.9% of the cells in vitro, inside the human body. And they're determined from a plate count for the MIC. Techniques are precise, but they're very labor intensive, and they're very, very expensive, and usually done when developing the antibiotics in the first place. This is the minimum inhibitory concentration, and you can see that we have organism A, B, and C, and we add the organism in a reducing concentration, so we can see at what point in time it eliminates the organism growth. In this case, it's 0.06. In this case, it's 0.5. In this case, it's 8.0. So you can see that it can occur at a very different rates depending on the mechanism we're talking about. There's also a conventional disc diffusion method. There's a disc called the Kirby-Bauer disc diffusion test. And this is routinely used to determine the susceptibility of bacterial strains to antibiotics. And so the standard concentration of strain is uniformly spread on an auger plate. The disc containing different antibiotics are placed on the surface. So it's a great big plate. It's about all 5.5 inches, 6 inches across. The diameter is about that. And so there's a machine, we hold on the top of it, and we push the machine down like a little plunger, and it releases all these discs. And each of these discs is infused with a different antibiotic. And by looking at the resistance and the effectiveness of certain antibiotics, we can make some decisions about not only how we treat them, like a culture sensitivity, so we see what it's sensitive to, but sometimes we can identify which strain we're talking about. So the drugs diffuse outwards and establish a gradient. Resulting zone of inhibition is compared with specially prepared charts to determine whether the strain is susceptible, intermediate, or resistant. Now, drug characteristics may be taken into account, for example, molecular weight, stability, that kind of thing. Now, chemical modifications of susceptibility testing, they're long and they're involved. They're less labor intensive, and they often give fast results. One automated system determines the growth rate via turbidity. So they're putting cards, interpret results, determine the mix in 6 to 15 hours. The test is modification of this diffusion test, and uses a strip with the gradient of the antibiotic. So we have this disc, and there's a strip, and it's more, the antibiotic concentration is greater as you go to the other strip. So we can see at what point that the antibiotic is effective against the bacteria or the antimicrobial, microbial that we're trying to use it against. We can measure the concentration of antimicrobial drug in the blood or other body fluids. Some toxic levels may be monitored to ensure safety. Diffusion bioassay compares the known concentrations with patient samples, and it produces a standard curve, and the comparison yields the concentration that's most effective, or at the point where the toxicity level is too high to use. Now, resistant antimicrobial medications, with the increasing use of antibiotics, there's a misuse selects for resistant microorganisms, and that's the problem. Only 3% of Staphylococcus aureus originally were resistant to penicillin G. You could say penicillin over the top of them 3 times and it would disappear. Now about 90% are resistant to penicillin. Isn't that interesting? Hundreds of tons are used each year to treat them. So antimicrobial resistance is alarming. The impact on cost, complications, and outcomes of treatment is pretty significant. because the antibiotics we have to use in place of cheap penicillin are more expensive. They have a higher, they have a more probable toxicity levels, and so they can create greater resistance to the microbe. Dealing with the problem requires understanding the mechanisms and the spread of resistance and the proper use of antibiotics. Now, the mechanisms of acquired resistance are antibiotic inactivating enzymes, so penicillinase, chloramphenicol, acetyltransferase. All of those block the effect of penicillin. There are alterations of the target molecule. There's a minor structural change that can prevent the binding, so PBPs, beta-lactam antibiotics, and ribosomal RNA macrolides or chains are no longer effective. Decreased uptake of medication, changes in the porin proteins of the outer membrane, the gram-negatives, can block the intake of a given antibiotic. So those can all be part of that. You can have increased elimination of medications, so efflux pumps in a microorganism removes the compounds from the cell so quickly it doesn't destroy the cell. Increased production of pumps allows faster removal. There can be structural changes which can influence the range of antibiotics. So resistance of this type particularly are worrisome because they might allow resistance to multiple antibiotics, not just one antibiotic. We also get acquisition resistance, which is spontaneous mutations, and they can occur during replication. Now they happen at a low rate, but they can have a significant effect. Just a single base pair can change a gene encoding a ribosomal protein which yields resistance to, for instance, streptomycin. In a population of 10 to 90 cells, at least one likely has had that mutation. If streptomycin is added, only that cell and progeny will replicate, yielding resistant populations. And the bad part is these organisms can then share that knowledge with other organisms. So spontaneous resistance to antibiotics with several different targets, multiple binding sites is less likely. So we use combination therapy in many cases of multiple antibiotics. So basically, it's unlikely that cells will simultaneously develop resistance to multiple antibiotics at the same time. There's a case called gene transfer, and that's the use of plasmids. Gene encoded with resistance can spread to different strain species and even genera, so even different genuses. Most commonly thought conjugate transfer of R plasmids, which often carry several resistant genes. The resistance can originate through spontaneous mutations. It may also originate from the soil microbes that naturally produce the antibiotic, and the gene coding for enzyme that modifies aminoglycosides likely originated from the Spectromyces species that produce the antibiotic. So sometimes the mutation piece, it's not a mutation, it's just a return to the cycle, the life cycle. Examples of emerging resistance are enterococci. They're part of the normal intestinal microbiota, and they're common cause of healthcare-resistant associated infections. Intrinsically, they're less susceptible to many antimicrobials, and the PBPs have low affinity to many beta-lactam antibiotics. Many have R plasmids, and some code for resistance to vancomycin. They yield vancomycin-resistant enterococci, which is transferable to other microbes. And vancomycin is often an antibiotic of the last resort when we're talking about infections, so that's kind of important. Enterobacteriaceae intrinsically are resistant to many antibiotics. Their outer membrane prevents entry. Some enterics developed ability to produce beta-lactamases, and some further developed the ability to produce extended spectrum beta-lactamases, which resist cephalosporins and astrinones, and in addition to penicillins. The more recently, carbapenem, this is hard to say, strains are found. They're resistant to clearly all antibiotics. The carbapenems, I can't say that, they're last resort for ESBLs, but are inactivated by this enzyme. So that's kind of an important thing to know. Now, mycobacterial tuberculosis requires a long treatment. It's a very slow grower. And over that time, it can become resistant to first-line antibiotics via natural mutation. So large numbers of cells are found in active infections, so likely at least one cell has developed a resistance. So in that case, we use what's called a combination therapy is therefore required, as I said earlier. Often it's a 6 months or up to 12 months of treatment is necessary due to the slow rate of growth, and many patients don't comply, unfortunately, because antibiotics can sometimes are setting into the normal system. The multi-drug resistant M tuberculosis is resistant to two favorite first-line antibiotics like isoniazid and rifampin. Now, directly observed therapy can prevent emergence, if you will. So extensive drug resistance for M tuberculosis of the greater concern because it's additionally resistant to the 3 or more second-line antibiotics. So it's starting to develop a resistance. When what used to be that tuberculosis can be treated efficiently, That took a long time, but efficiently with these antibiotics. But now we're seeing more and more resistance, obviously. The other one is Neisseria gonorrhea, which at one time was very simple penicillin. What happened is during the Vietnam War, there was a high rate of gonorrhea, and they used penicillin like crazy, and they developed strains, and sometimes some people feel the strains were actually actively grown by the North Vietnamese, and then passed on to prostitutes so they could infect soldiers, but that their symphylated penicillin went away. And so some strains developed resistant penicillin just through natural mutations, but others required a plasmid that encoded the production of penicillinase. So we often have to use cephalosporins as a reliable treatment, and a combination therapy is used now. We tend to use a combination of two things. Now, Staphylococcus aureus is the bacteria that we grow like a flower in our own garden. The increased resistance is based on our increased use of stronger antibiotics, stronger types of antibiotics, and we basically created this immunity by our misuse. We used it improperly, and we didn't use it thoroughly when we treated the infections. So the common cause of healthcare-associated infections, most strains are resistant to penicillin. They encode penicillinase. The new strains are recently emerging have PBPs with low affinity all beta-lactam antibiotics, methicillin and others. And it's called methicillin-resistant Staphylococcus aureus, or MRSAs is the short term, if you will. Now, methicillin-resistant Staph aureus is healthcare-associated, is resistant to a wide range of antibiotics and usually treated with vancomycin. But we're starting to see resistance to vancomycin, so we have strict guidelines to halt the spread of those vancomycin intermediate Staph aureus and vancomycin-resistant Staph aureus strains. So we're trying to sort of manage those. Also, there's community-acquired MRSA, which is currently treatable. Streptococcal pneumonia is has historic susceptibility. Some recently acquired penicillin resistance we're seeing. Used to be used penicillin against strep pneumonia very easily, but it's producing PBPs with lower affinity, likely via transformation from other Streptococcus species. So this immunity is being transferred from the different strep species and maybe their staph species. So there's a slowing emergence and spread of resistance. And I wouldn't say slow. I would say it's gaining speed. So it requires cooperation from everybody globally. Responsibilities of physicians, healthcare workers are to increase efforts to identify the cause of infection, only prescribe the suitable antimicrobials that are appropriate, and educate patients about proper use of antibiotics. Responsibility of patients to carefully follow directions, even if inconvenient, and essential to maintaining adequate blood levels of antibiotic over time. Skipping a dose may reduce levels, allowing less sensitive microbes to get a chance to grow and spread and become resistant. So failure to complete treatment may not kill these sensitive, similarly allowing subsequent spread of the microbes. So taking your treatment all the time properly. Now, slowly emerges the spread of resistance. The importance of an educated public, like I said, antibiotics are ineffective against viruses. They do not cure the common cold. As a PA, I can't tell you how many times I had to sit in an office and explain that to patients who were very angry and didn't give them an antibiotic for their cold. Misuse selects for antibiotic-resistant bacteria in normal microbiota, they can eventually transfer to pathogens. So we've trained our normal flora to be resistant, which pass on that information to more aggressive pathogenic bacteria. Global impacts to the use of antimicrobial medications. Overuse is a worldwide concern. Resistant microbes recognize no political boundaries. Antimicrobial antibiotics are available without prescription in many parts of the world, which allow improper use. Like you go to Mexico and you could get, you go to the pharmacia and get prescriptions for penicillin and ampicillin and things like that. Antimicrobial antibiotics used in animal feeds at low levels to enhance growth. Selects for antibiotic-resistant microbes, so antibiotic use in the food we eat, particularly meat products, and develop resistant salmonella strains, which are linked to the animals. So we're causing this for our own self. Here's the nice list of resistant antimicrobials and the comments, if you will, the microorganisms and what we're seeing. So I'll let you look at that on your own. Now, mechanisms of action to antiviral medication. So viruses are difficult to target selectively. They rely on the host metabolic machinery, so they don't have cell walls, ribosomes, or other structures that can be targeted by antibiotics. So many encode polymerases, which represent potential targets. Scientists are trying to develop antiviral chemicals that interfere with viral replication. The current option, effective only against specific types of virus, and none eliminate latent infections. So if they have a chronic infections like herpes, or a chronic infection like HIV or HPV, there's no antibiotic to eliminate those. This is a list of those, list of target class, if you will, and a list of comments, and I'll let you go through those also. Now, the best way to prevent viral injury, that's one of the ways we treat. There are nuclear chemicals that prevent the viral from entry into the host cell, and the N-fluvaritide binds to an HIV protein and promotes fusion of viral envelope in the cell membrane, almost like interferon. Maraviroc blocks the HIV coreceptor CCR5. So interfere with the viral uncoating, that means that once the viral enters the cell, it stops it from uncoating the nucleic acid. So the nucleic acid must separate from the protein coat. There are two chemicals that target this step, amantadine and rimantadine. They block influenza A viruses, they prevent the reduced severity. The viral strains are easy to develop resistance, so its usefulness is limited. So people that get influenza A or B, if you will ask for these, but sometimes it's not effective once they've had the disease for a period of time. Now, we also have interference with nucleic acid synthesis. So nucleoside analogs, they structure similar nucleosides, phosphorylated in vivo by virally encoded or normally cellular enzymes to form a nucleotide analog. Incorporation in nucleotide chains can stop nucleotides from being added or alter base pairing properties to occur from the virus genome. So selective toxicity, since virally encoded enzymes are more likely to host cell polymerases to incorporate them, so there's more damage done to rapidly replicating viral genomes, but they're only effective against replicating viruses. Most of these are reserved for severe infections, and because they have significant side effects. Acyclovir is the exception. We use that to treat herpes virus with little harm to the uninfected cells, since it's only converted by virally encoded enzymes present in the infected cells. But acyclovir does not work intracellularly, it works extracellularly, which means acyclovir does not kill the virus inside the cells. So acyclovir for herpes, for instance, kills the active herpes outbreak, but does not kill the herpes virus that's located inside the eukaryotic cells in the humans. Another nucleoside analog is ganciclovir, which is used to treat life or life-threatening diseases like cytomegalovirus infections in immunocompromised. Like ribavirin is used to treat respiratory syncytial virus infections, RSV, in newborns. Nucleoside reverse transcriptase inhibitors are used to treat HIV, and so the virus rapidly develops mutational resistance, often used in combination with other anti-HIV chemicals. NRTIs include zidovudine, AZT, as you say, didanosine, which is DDL, and lamivudine, which is 3TC. Two of these are often used. Two of these three are often used in combination. Now, the non-nucleoside polymerase inhibitors, they inhibit viral polymerases by binding the site other than nucleotide binding site. For instance, Fascrnet is used to treat ganciclovir-resistant CMV and acyclovir-resistant HSV. Non-nucleoside reverse transcriptase inhibitors, like NNRTIs, inhibit the reverse transcriptase by binding the site other than nucleoside binding site. They're often used with nucleoside analogs to treat HIV infections. Include nevirapine, delavirdine, and efavirenz. And so they are just different versions of that. There's some that prevent genome integration. They offer new options for treating HIV infections. They inhibit the HIV-encoded enzyme integrase, and it prevents the virus from inserting its DNA copy of genome into the host cell. Another a good example of that is raltegravir, which is a first approved chemical of this class. And raltegravir is a first approved chemical for this. So we're starting to see that as an addition to the cocktail, the HIV cocktail we're using for people who have active HIV. To prevent assembly and release of viral particles, the virally encoded enzyme required for assembly release, we have protease inhibitors are virus-specific. During replication of HIV, several proteins are translated as a polyprotein that must be cleaved. It includes idinavir, ritonavir, sequinavir, and dalfinavir. And telpravir, both cefpravir and simapravir are approved to treat hepatitis C, and we're starting to see that treatment also. Hepatitis C, which is the biggest, probably have epidemic proportions in our elders because we didn't know about it before. You also have neuraminidase inhibitors. Enzyme encoded by influenza virus is needed for release. So that's a very effective direct help for that. Hold on a second. Okay. I'm sorry, I can find my place here. So nucleic acid synthesis, we have non-nucleoside polymerase inhibitors. They inhibit viral polymerases by binding a site other than nucleotide binding sites. So foscamet is used to treat glycophore-resistant CMV and acyclovir-resistant HSV, which I think I said earlier. We talked about non-nucleoside reverse transcriptase inhibitors, and they are often used to treat the HIV, which I said before, and I've explained that. I've done this before, so I've repeated myself, and I apologize. They have some that prevent genome integration. They offer a new option for treating HIV infections. They have an HIV encoding enzyme integrase prevents the virus from inserting DNA copy of the genome in the host cell. And I did this all KASC. I've done this also, so I apologize. I've rerun myself. I apologize. So now we're at the right side. So eukaryotic pathogens are difficult to target. They more closely resemble human cells than bacteria, and we use plasma membrane synthesis and function, if you will. Polyenes are produced by streptomyces. They bind to ergosterol. They cause the membrane to leak and toxic to humans. Azoles inhibit ergosterol synthesis. They cause the membrane to leak. They may have side effects to humans. And alliminines inhibit the enzyme in ergosterol to synthesize pathways. So what happens is these antifungals can be quite toxic at certain points. So you got to be very careful with them. The mechanisms of antifungal medications include cell wall synthesis. The fungal cell walls have some components animals lack, and the echinocandins interfere with synthesis of beta-1, 3-glucan, and it causes cells to lyse. So sasfofungin is the first to be approved. It also affects cell division. So griseofulvin targets the cell division, interferes with the tubulin production. Remember, tubulin is the protein that we see in the microtubules inside the cells. It's found in eukaryotic cells. Selective toxicity may be due to a greater uptake of the fungal cells. We have the antifungals that work on nucleic acid synthesis, common in all eukaryotes, generally poor chemical target. Flucytosine is taken up by yeast cells, converted to active form. They have nucleic acid synthesis, and they have side effects. So the other effect you see here, here's some of the characteristics of antifungal medications. There's the list. There's the comments. I'd like you to go through those in your textbook, but I won't go through those here. Here's an anti-helminth. These are actions of anti-protozoan and anti-helminth medications, and these are a list of medications we use and the comments associated with that. So mechanisms of action of anti-protozoan and anti-helminth. There's relatively little research and development because most parasitic diseases are concentrated in poor areas of the country and where medications are really unaffordable. So most chemicals interfere with the biosynthetic pathways of the protozoan parasites and the neuromuscular function of the worms. So that's their direct effect. And again, here's some characteristics of the anti-protozoan and anti-helminthic medications you can see here. So we've just gone through the antibiotics, if you will, antimicrobial medications as treatment. And this is chapter 20, and this will be the last lecture within this series. Thank you very much.